In our daily life, we used to see when we heat a metal, at first it appears in a faint red and it becomes intense red when we heat more. And upon further heating, it becomes yellowish orange and finally it becomes yellowish white for the intense heating. What is the reason for this transition of color when a metal is heated? This question made several scientists in 19th century sleepless, and this question gives rise to the birth of quantum mechanics and modern physics. So this is called blackbody radiation. Let's dwell deep into this question. For to understand the nature of radiation emitted from a hot object, one has to understand the Planck's radiation formula for blackbody. So before proceed to the discussion of Planck's formula for blackbody radiation, one has to understand what is blackbody and blackbody radiation. So a blackbody is an idealized object that absorbs all the radiation incident on it. When such a body is heated, it emits radiation of all the wavelength at thermal equilibrium. So ideally means practically there is no such body as black body, but one can construct a practical black body using the following setup. In that setup, you have to take a hollow cavity with small hole in it, and this inner surface of the cavity is highly polished such that if light ray enters into this body, it undergoes multiple reflection and finally dissipates all its energy into the cavity itself, and before it leaves the cavity, it its energy is completely dissipated into the cavity itself, means no light is being emitted. So it acts as a perfect absorber. Whatever rays that you incident on the hole, they will be completely absorbed by the setup, cavity setup. Next, if you heat this hollow cavity, radiation of all the wavelength will be observed. So that in the spectral wise intensity distribution one can obtain using the spectrometer. So the spectrometer will give the intensity at, let's say, lambda. If you ask the spectrometer the intensity at this lambda, it will give the intensity at a particular lambda that you want. If you ask some other lambda dash, it will give the intensity corresponding to this lambda dash. So likewise it decomposes the total intensity spectral wise, lambda wise or frequency wise. Okay, this is the typical experimental blackbody spectral energy density distribution. So you can see at a particular temperature at thermal equilibrium, this is my energy spectral energy density distribution, and you can see a pronounced maximum at a particular lambda, and above this lambda in the intensity decreases monotonically. So intensity at very high lambda and very low lambda, it is almost zero, and it is maximum at a particular lambda, and so it is also a kind of continuous distribution. So we can get intensity of all the wavelength continuously. Okay, next, if you increase the temperature of the black body by inputting more energy, it will settle in different equilibrium condition, and at that high elevated temperature you can see the peak of the energy density distribution shift towards the lower wavelength side. Overall intensity of spectral density increases. In addition to this increase, it also possesses some kind of shift in the peak density lambda at which the peak occurs, that is shifting toward the lower wavelength side, and further increment temperature of the black body leads further decrease of the peak distribution towards the left side of lambda, means lower wavelength side. Here the quantity U of lambda comma T represents the radiation energy emitted per unit volume and unit frequency range, and it's a function of lambda comma T. So there were many scientists in the mid of 18th century who had tried to give the theoretical explanation for the observed black-body spectrum. Among them, the notable are the Wien's. He gave the Wien's law, and this is his spectral energy density expression. As you can see, it's a function of 1 over lambda raised to 5, means lambda raised to 5, and this his law fits the observed energy density expression only in the low wavelength regime, and it miserably fails in the high wavelength regime. And the next notable person is Raleigh and Jeans. He focused on understanding the nature of electromagnetic radiation inside the cavity, and he considered that radiation to consist of standing waves having temperature T with nodes at the metallic surfaces. And these standing waves, he argued, are equivalent to the harmonic oscillator, as they result from the harmonic oscillations of huge number of electrical charges, that is the electron that are present in the walls of the cavity. And he derived this expression for the energy spectral energy density of black body. As you can see, it's a function of nu raised to 4. This lambda can be written in terms of frequency, so it will be in the numerator, there will be nu raised to 4. So clearly you can see if nu tends to infinity, spectral energy density also should goes to infinity, but that should not be the case experimentally. As you can see, when nu tends to infinity, means nu tends to infinity, you can see spectral energy density should goes to 0, but this is a clear violation of the experimental observation, and it also leads to the ultraviolet catastrophe. Means if nu tends to infinity, energy density also goes to infinity. That means the black body contains infinity amount of energy. If it has infinity amount of energy, it won't be in a particular place. Okay, so this is called ultraviolet catastrophe. And so now in the year 1900, Blanks gave the correct explanation for the observed black body spectrum, and his formula is called Planck's black body radiation formula. So he derived his formula based on the hypothesis called Planck's quantum hypothesis, and as per his hypothesis, the cavity wall contains an oscillator, charged oscillator, coupled charge oscillator, and this oscillator, whenever interact with the radiation, it's not continuous in energy. Means this interaction happen discontinuously. So the atoms of the walls of the black body behaves as an oscillator, into each having its own characteristic frequency, and his first postulate is an oscillator can have only discrete energy. This oscillator here can have only discrete energy, not continuous range. Means if it take h nu of energy at some particular instant, at some other instant, it will either take 2 h nu or 3 h nu and so on, not in between 2 and 3 h nu. So the next hypothesis he made is, so the whenever the oscillator emit or absorb energy, that should be in terms of quanta of energy, not continuously again. So the absorption, if the oscillator takes some energy and goes to the higher excited state, so it we need to supply an amount of energy called h nu, quanta of energy. And if emission takes place, again it will be in terms of the quanta of energy h nu. So having said this, let's proceed to the derivation of Planck's law. So the Planck's derivation and Wien's and Rayleigh's derivation all are differing in finding the average energy expression. So let's first find what is the way how the Blanks found this average energy. So As we know, this cavity valve contains large collections of oscillators, each are having different frequency, so they will have different energy. Okay, now how to find the average energy that is sitting here in this expression. The question is how to find the average energy of the oscillator E bar. So to find that, so I'm going to assume that I have n number of total oscillator, and capital E is my total energy of all the oscillator, and E bar is the average energy of the oscillator. So my E bar average energy I can represent in terms of E by N, means total energy by number of oscillator, that will give the average energy. Now the question is how to find E and N. To find the average energy of the oscillator, I am going to do some kind of grouping with the available energy levels of the oscillators of the cavity wall. This grouping is such that where N0 is the number of oscillator that are having the common energy of 0, whereas N1 is the number of oscillator that are having the common energy of h nu, and N2 is the number of oscillators that are having energy of 2h nu, and so on. So the total number of oscillators can be found by simply adding all such oscillators in each individual energy levels. So the from Maxwell-Boltzmann distribution, I can find the population in the nth level using the ground state population using the Boltzmann factor using equation number 4, and substituting beta is equal to 1 by kt, I can rewrite equation 3 in the following way: n naught into exponential minus beta h nu, this way. Then taking out n naught commonly, I can write, and substituting for exponential minus beta h nu as x, I can rewrite equation 6 in this simplified form, and equation 8, this series can be written as the binomial expansion of this function 1 over 1 by x, and substituting there I can find the total number of oscillator in the cavity wall using equation number 10. So here for your reference, I have added the generalized form of binomial expansion, and in this expansion, if I replace x by minus x and n by minus 1, I will get exactly this series. So this series is a converging series if x is less than 1. So otherwise it will be a diverging series and the number of oscillator would go to infinity. Okay. So now how to find the total energy of all the oscillator. So for that I am going to do the summation where Ni is the number of oscillator in ith energy level, and epsilon I is the energy of the ith level, and epsilon I energy of the ith level is simply I times h nu. So expanding this we can get this term, and substituting for e raised to minus beta h nu as x, and we get equation 13 in the simplified form, and if you take out x you will get 1 plus 2x plus 3x squared into this term. So now how to find the summation of this series? So this series is nothing but the derivative of the previous series that we considered, 1 over 1 minus x, and if you take differentiation you get exactly this form. So this series can be represented as the derivative of this binomial expansion of this function. If you take the derivative you will get exactly this, and substituting this into equation 15 we get the total energy as this equation 17. Substituting this energy into the expression for average energy, one will get this expression, and simplifying this and substituting for the value of x we get this, and this is the final expression for average energy. So substituting again this into the expression for energy density, spectral energy density expression. So this energy, average energy, has to be placed here, and you get the spectral energy density as this. So finally we get this as the spectral energy density of blackbody radiation in terms of frequency. So this is called blackbody radiation formula in terms of frequency, and the same can be obtained in terms of wavelength by using this conversion. So u nu can be expressed in terms of u lambda by putting a minus sign in front of that, because nu and lambda as complementary to each other, and expressing d nu in terms of d lambda, one will get the expression for energy density in terms of lambda as this. So finally we get the energy density expression, blackbody energy density expression in terms of lambda. And so this is the formula which exactly simulates the experimental observations, and this correctly fits the observed experimentally observed blackbody energy density expression in all wavelength and all frequency range. So this will smoothly merge with the Wien's law and Rayleigh-Jean's law in the appropriate limiting cases. One can see if lambda is low, means in the low wavelength regime, this factor, exponential factor, will be much higher than 1. So in this expression one can neglect this 1 and write this expression. When you take this expression to the numerator, you get the energy density expression as this is exactly the Wien's energy density formula, and it's directly proportional to 1 over lambda raised to 5. Similarly, in the high wavelength limit, this Planck's radiation formula will converge to Rayleigh-Jean's formula in the following way. In the high lambda limit, this will be lesser, means this value will be less, and one can approximate this, expand this in Taylor series expansion, and neglecting orders greater than the quadratic order, and retaining up to only the linear term, one will get this expression, and this one and the one here will get cancelled, and numerator only this term will be there, and simplifying this, one get the spectral energy density in the high lambda limit as this. So this is the Rayleigh-Jean's expression for spectral energy density. So that's all. Thank you.